Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at the topic of the Doppler effect that forms part of your paper 1 physics exam. Alright guys, if you need assistance tutoring, please do visit our website www.mvtutors.co.za and make a booking. Alright, so what is the Doppler effect? Well, I try to illustrate here with my stick figures. Alright, so imagine you have an ambulance there, and your friend is over there on this side, and you are on the other side. So basically, where you are standing, the vehicle or the ambulance is coming towards you. So as it comes towards you, as you can see here, the sound, you'll hear a much higher sound, okay, a bigger sound, or rather a bigger pitch. All right, because as it moves towards you, the sound waves it forms, they become compressed as they come towards you. Okay, and the more compressed they are, as I've said here, the less or the lower the wavelength. So you see the distance here between the waves, it's quite less. So the lower the wavelength, the higher the frequency or the pitch that you're going to hear. So you're going to hear more sound. But your friend over here who's on the other side, as the ambulance leaves him or her, well, the wavelength becomes bigger, okay? And as the wavelengths become bigger, the lower the frequency and the lower pitch heard by the listener. Okay, so that's basically the concept of the Doppler effect. You have a source of a sound and you have a listener. And the frequencies heard by the listener depends on whether the source of sound is moving towards or away. All right, so then we can come and define what the Doppler effect is. Okay, so let's write down the definition. So the Doppler effect is the change in frequency. So first of all, it is the change in frequency or pitch of the sound. The sound heard by or detected, let's rather use the word detected, of the sound detected when the wave source it could be a siren from an ambulance or the police car or whatever, okay? So the change in frequency or pitch of the sound detected when the wave source and observer, listener, move relative to each other. Okay, so there will be a change in frequency or pitch as the source and the detector or the listener, the observer rather, they move relative to each other. And like I said, if the source moves away, you will hear less sound. And if the source moves towards the observer or the listener, then it will be magnified. The sound will be magnified. And we use the following equation, okay, to calculate. So you have the frequency of the listener or observer, then the frequency of the source, okay? Then you have the speed in air, all right? Most of our examples are in air, or you could have it in water. It depends, but they'll always give you the speed of sound in air, okay, or the speed of sound in water. And then plus minus the velocity or speed of the listener over the velocity of air or water plus minus the velocity of the source. So like I said, they will give it to you if it is the velocity of sound in air, that is 340 meters per second, and in water it's 1,500 meters per second. Now, how do you know whether to choose plus or minus? Okay, so it depends. Is the source moving away? Is the listener moving away? Or are they moving close to each other? Or is one still and is one moving? Okay, it depends. All right, so here, looking at our sketch, or the sketch that I drew, I'm assuming that both your friend, you and your friend, are still. Okay, so the listener on this side, when the source is moving away, is stationary. Okay, so in that case, according to that equation, the velocity of the listener, that will be 0. Okay, and they are stationary. All right, so it'll be plus or minus. And then the velocity of the source, okay, that is the source of where the sound is coming from, is moving away from the listener in this case. So you will have a plus when it's moving away. Now, on this side, the other side, where the source is moving towards the listener, you put a negative there. And the speed of the listener was 0 because they're stationary. So basically, if the listener is moving towards the source, you use a positive. And if they're moving away, you use a negative. If the source moves towards the listener, you put a negative. And if they move away, you put a plus. So it depends. The source and the listener could both be moving away or towards each other. Or one could be stationary and the other could be moving. Okay. And then let's just talk about the frequency of the wave. So for you to calculate the frequency of the wave, that'll be 1 over the period. And frequency is measured in hertz. If you want to calculate the period, now period of the wave is the time it takes for one complete wave to pass a fixed point. What do I mean by that? If you have a graph like this, and you have waves in succession. Okay. So the distance, so this will be one wave. Okay, the one that's thicker. Okay, so that the period there, so this would be your period. Okay, T. The time it takes to complete a wave. So that's one wave there. Okay, so that is your period. That's how you get it. And if they haven't given you frequency, but period, then you can calculate the frequency from the period given. And it's normally given in seconds. Then you have the speed of a wave. Okay, so if it is the speed of a wave in the air, you already know that it is 340 meters per second. If it's in water, it will be 1,500 meters per second. So it depends really what they've given you. And if they've given you a wavelength, which is measured in, wavelength, which is measured in meters. So if you have a speed and you have the wavelength, you can also get the frequency. Okay, so yeah, I think that is basically the theory behind the Doppler effect. Now let's go to the calculations. All right, so question 6. So Doppler effect is normally question 6 of your paper 1 exam. Now it says the alarm of a vehicle parked next to a horizontal road goes off. Okay, I'm going to just attempt to draw a vehicle. So you have a vehicle here. Okay, it is parked, guys, so the velocity is 0. It's not moving. All right, and it is emitting sound with a wavelength of 0.34 meters. So we already know wavelength is 0.34 meters. Okay, so I'm just going to say that's the sound source, so it's emitting sound. Okay, a patrol car is moving at a constant speed on the same road. The driver of the patrol car hears the sound with a frequency 50 hertz lower than the sound emitted by the alarm. Okay, guys. So for now, your source is stationary. Okay. When your source is moving away from a listener, they will hear a lesser sound or lesser frequency. Okay. But in this case, the source is stationary. So this vehicle, this patrol car that's moving at a constant speed, must be moving away from the source. Okay, so it could be a patrol car going that way. Okay, so it's moving away, all right, and therefore the sound or the waves, they are bigger. Okay, we have bigger wavelengths because it's moving away, we're expecting less sound to be heard. And they did say that the frequency, so if let's say the frequency this side is X, the frequency that will be heard by the patrol car will be X minus 50. Okay, take the speed of sound in air as 340 meters per second. Okay, cool. Now, state the Doppler effect in words. Guys, we already discussed this. Basically, it's the change in frequency or pitch, okay, of if you have the source of the sound and you have a listener moving relative to each other. Okay, so as they're moving relative to each other, you will get a difference in pitch and sound. Okay, a proper way of saying it is how I've written it. Change in frequency or pitch of sound detected when the wave source and observer or listener move relative to each other. All right, so that's the Doppler effect. So yeah, we're done. Now, 6.2. Is the patrol car moving or driving towards or away from the parked vehicle? All right, so it is moving away, like I said, okay? Because the sound or the frequency heard or experienced by the patrol car is less, it's 50 hertz less, okay? That would be the reason. So the frequency is less than that of the stationary vehicle, okay? And also the wavelengths, they're bigger if that's the case, okay? So yes. Then 6.3, it says calculate the frequency of the sound emitted by the alarm. Okay, remember that equation where I said the speed of sound in the air, okay, is equal to your frequency times your wavelength. And they have given us the wavelength, guys. It was 0.34. And we have the speed of sound. So 340 meters per second. Frequency is our unknown. And we have 0.34 meters. Okay, so our frequency will then be 340 divided by 0.34. Okay. We can use our calculator. If you can already see it, then you can go ahead and just write it. It's about 1,000, right? So 340 divided by 0.34, that'll be 1,000 hertz. Okay, so 1,000 hertz. And guys, let's just go back. The frequency of the sound emitted by the alarm. So that is the frequency of the source. If that is the frequency of the source, what is the frequency of the listener? They said the frequency of the listener is 50 less than that of the source. So the frequency of the listener in this case would be 950 hertz. Okay, this is extra information. You could have stopped there. Now finally, sorry about the background noise, guys. Okay, finally, 6.4. The patrol car moves a distance x meters in 10 seconds. Calculate the distance x. Okay, so the equation I'm thinking about, if I've been given time, okay, I go back to my equations of motion where delta x is equal to the velocity. Remember, velocity is in meters per second. So if I want meters, I would have to multiply it by time. Okay. And I will get my answer in meters. So I need the speed, all right, of the patrolling car. Remember, the speed of the source of the sound was 0 because it was stationary. And the question does ask, the patrol car moves a distance x meters in 10 seconds. So we need to calculate that distance of the patrol car. Now comes in the equation of the Doppler effect. So you have the frequency of the listener, and then you have the frequency of the source. Okay, I'm just trying to remember the equation. You have the speed of air, and you have the speed of, is it the listener? Let me just check. Yes, the speed of the listener. the speed of the listener, which is the patrol car, again the speed of air, and then the speed of the source. We know that it's 0, right? So guys, plus minus, what's happening? The source is stationary, okay? So doesn't matter, it's going to be 0. But the listener is moving away. And what did we say about the listener moving away? We're going to use a negative. Okay. Yay. So negative. Now we have this frequency of the listener, which is 950. The frequency of the source, which is 1000. The speed of air is 340. Our unknown speed of the listener. And then we have 340 because the speed of the source is 0. Alright, so this is where maths comes in. Now we have 950 over 1000. This 340 is going to come this side. Then we are left with 340 minus the speed of the listener. Alright, and then I'm going to take, so I have negative, and then I have 950 over 1000 times 340 minus 340. Alright, and then finally we can check what the speed of the patrol car is. Oh, wrong thing. Okay, so we have 950 over 1000, okay, times 340 minus 340, and we get negative 17. Okay, remember we have negative that side, so negative 17, and then finally our speed is 17 meters per second. Okay, now remember guys, the question was how far? The distance, you need x, okay? So x, we did say it's going to be velocity times time, and the time was 10 seconds. So we have 17 times 10, which is 170 meters. And yeah, that's it. Let's try another example. All right. So both these questions, one is from 2018, one is from 2019. I forgot which is which. So yeah, but it doesn't matter as long as you get the questions. All right, so the siren of a police car, which is traveling at a constant speed along a straight horizontal road, emits sound waves at constant frequency. All right, detector P is placed inside the police car, and detector Q is placed next to the road at a certain distance away from the car. The two detectors record the changes in the air pressure readings caused by the sound waves emitted by the siren as a function of time. The graphs below are obtained from the recorded results. Okay, so we have graph A. So there's detector in the car. Okay, so this, guys, the detector in the car, the frequency of the detector in the car will always be the frequency of the source of the sound that comes from the car. So it'll always, if the car has a frequency of 100, detector P will always have a frequency of 100. Detector Q, however, that will depend. If the police car is moving towards Q, then it will detect a higher frequency. If it is moving away from Q, it will detect a lower frequency. Okay, so now let's see. So for the detector P in the car, that will give you your frequency of the source. Okay, and then Q, that will give you the frequency of the listener. And remember guys, frequency is equal to 1 over period. And a period, remember I said one wavelength complete. That gives you the period. Okay, and please be aware that the time is times 10 to the power minus 4 seconds. Okay, and again here you will get your period from this one full wavelength. If you wanted to use another full length, it would be from this side to that side. So you would say 25,5 minus 8,5. You're still going to get 17. Okay. So yeah. Now what are the questions saying? Alright, 6.1. Different patterns are shown above for the same sound wave emitted by the siren. What phenomenon is illustrated by the two detectors showing the different patterns? Okay, this phenomenon, guys, is called the Doppler effect. Alright, then it says the police car is moving away from detector Q. Okay, now use the graphs and give a reason why it can be confirmed that the police car is moving away from detector Q. Remember at the beginning that image I drew of the stick figures? When the source is moving away from the detector or observer or listener, the wavelengths are big. Okay, when it is moving towards the listener, the wavelengths are shorter. All right, so comparing these guys, here you have, for it to complete one wavelength, it takes 17 times 10 to the power minus 4 seconds. But here, it takes 18 times 10 to the power minus 4. So the wavelength here is bigger. The wavelength of the listener, bigger than the wavelength of the source. And if that's the case, it is moving away. Okay, so yes, it depends on the wavelength size. Okay, so using the graphs, give a reason. We know that the wavelength of the listener is higher. Therefore, the frequency will be low. Therefore, it's moving away. Okay, you can write it in nicer words. Now it says calculate the frequency of the sound waves recorded by detector P. Alright, so detector P, that is the one in the car. Okay, and we already said that frequency is 1 over period. Okay, and the period for one wavelength was 17 times 10 to the power minus 4 seconds. Okay, 17 times 10 to the power minus 4. And then we're going to get an answer in hertz. Okay, so that is the frequency of the source. Right, so using a calculator, we will say that 1 over 17, 17 times 10, what am I doing? 17 times 10 to the power minus 4, and that is 588. So, 588, comma 2353, blah blah blah, but we normally round up to 2 decimal places, so it's 588.24 hertz. Okay, right, and then now 6.4, use the information in the graphs to calculate the speed of the police car. Okay, remember it's moving at a constant speed. Again, using the Doppler effect equation, frequency of the listener is equal to the frequency of the source, and we're in air, so the volume in air, no, the velocity, oh my gosh, sorry guys, the velocity of the source and the velocity of the listener. Do I have it correct there? Let's just check. Yes. No, listener and source. I have it the other way around. Okay. Alright, so it is the okay guys, frequency of the listener, velocity of the source. Okay. Sure, I'm recording in the morning, so I feel like my brain is a little bit slow there. I'm using volume, then I'm saying frequency. It's actually velocity. Okay. Alright guys, so we have determined that the police car is moving away from the detector. Okay, so what did we say about moving away? We can go back to our notes. If the source is moving away, we're going to use positive. Okay. The listener was moving away, not the source. Okay, guys, so the listener is stationary. So, yeah, plus minus because it's going to be 0. But the source, the police car, it's moving away, so it's going to be a plus. All right, so we have the frequency of the source. Okay, I'm just going to put 1 over t as my frequency so that I don't lose. Due to rounding off, sometimes your answer can be a bit off. So the frequency of the listener, remember the detector, it had 18 times 10 to the power minus 4. So I'm just going to plug that there, 18 times 10 to the power minus 4. And this side for the source, we had 17 times 10 to the power minus 4. Just so that I know that I got a more accurate answer, okay, without using rounded off values. Then 340, again 340. Okay, so the listener was stationary. So yeah, I don't need to write anything. And then we're looking for the speed of the police car. All right, so here we are with maths again. So I'm going to take that, 17 times 10 to the power minus 4 over 18 times 10 to the power minus 4. Then I have 340 over 340 plus Vs. Okay, so I'm going to just turn it around, swap it. So I'm going to have 18 times 10 to the power minus 4 and 17 times 10 to the power minus 4. I could actually cancel that. But anyway, then I have 340 plus Vs and I have 340. Okay, simplifying it again, I'm just going to say 18 over 17 multiplied by 340 minus 340 is the speed of the source, or the speed of the police car. And then using the calculator, we're going to say 18 over 17 times 340 minus 340. Okay, and the speed is 20 meters per second. Okay, was that it, or did they ask us something more? Yeah, that's it. All right, guys. I also have another example, but I'm not going to put figures on. It's just what happens when sound is reflected. Okay, so reflection of sound. Okay, so what happens? Let's just say you have a submarine moving towards an object. Okay, so submarine looks something like that with its stuff there. Something like that. And it's moving towards a source or an object. Okay, so it is emitting sound waves. Okay, so it is moving. It's in water, by the way. So you know that the speed in water is 1,500 meters per second. Okay, so if it is moving towards the object, okay, what will happen is you have a frequency, okay, a certain frequency of the source. Then you have the frequency of the listener, all right, which will be higher than the frequency of the source, okay, and it's also moving at a certain speed, all right, but this one, the speed of the listener is 0. Okay, so you can calculate then, if we're looking for the frequency of the listener, okay, you can determine what the frequency of the listener is, provided you have this information, all right. But now, this object, as the submarine is moving closer towards it, this object is also, once the sound waves from the submarine move towards the the stationary object, the object will also reflect back those sound waves. Okay, so you have the sound coming from this side, the waves coming this side from the submarine, and you also have waves coming from the reflected from the object. Okay, so now you still have the frequency of the, okay, now this becomes the frequency of the listener because of those reflected waves. Okay, then you have the frequency of the source that you obtained there. So whatever you calculated there, that is what will happen. That will be the frequency of the source. You still have this submarine moving at that speed, the constant speed, and this is still 0. So again, you can calculate the new frequency of the listener. Okay, so this would be the submarine. And that listener there would be the object. Okay, so guys, if there is a reflection of sound, don't be scared. Just think about it. The source will emit waves. They will be reflected back. So I think the tricky part there is to acknowledge or see that the frequency of the object there that you calculated will be the same when it is reflected back. That is just the trick to this question. But if you want more examples, if you want me to put values here and see what the amounts will come or will amount to, please guys do visit our website www.mptutors.co.za to make a booking, and we will be happy to assist you. All right. So yeah, enjoy your day as I head to work. Bye.